Now that we've described average and instantaneous velocity, it's time to start talking about average and instantaneous acceleration. Velocity told us how quickly we changed our position. Acceleration tells us how quickly we change our velocity. So, for example, let's go back and talk for a moment in terms of cars. So, my car, when I have it sitting at rest, I'm traveling at a velocity of 0 miles per hour. But later on, I might be traveling a velocity of 60 miles per hour. That means that if I traveled for a time of 1 hour, I would go a distance of 60 miles. If I traveled for half an hour, I would go a distance of 1/2 of 60, or 30 miles. And if I traveled for 2 hours, I would go a distance of twice 60, or 120 miles. But what about how quickly I speed up? I have a car that may be able to go from 0 miles per hour to 60 miles per hour in 10 seconds. So in other words, that is an acceleration, an average acceleration, where I take the final velocity, subtract the initial velocity, and divide it by the change in time. So the acceleration of my car would be 60 miles per hour minus 0 miles per hour divided by 10 seconds. And that would give me 6 miles per hour per second. Now that's a decent but not particularly impressive acceleration. A really good acceleration would be a car that went from 0 to 60 in, say, 6 seconds. In that case, I would have an acceleration that was 60 miles per hour minus 0 miles per hour divided by 6 seconds, which would be 10 miles per hour per second. What do these mean? With my car, if I accelerate for 1 second, I will go from 0 miles per hour to 6 miles per hour. Or if I started at 20 miles per hour and accelerated for 1 second, I would go from 20 miles per hour to 26 miles per hour. By contrast, if I'm in the really nice Porsche that can go from 0 to 60 in 6 seconds, if I start at 20 miles per hour and I accelerate for 1 second, I will end up at 30 miles per hour. Notice this is often the real difference between different cars. I once drove an old Pinto that took at least 15 seconds to go from 0 to 60. But on the freeway, I could still pass Porsches because there was a speed limit and there was traffic. So I could still go 80 miles per hour. It just took me a long time to get there. So notice it's a very different concept, acceleration, compared to velocity. Velocity is how quick you're moving, how quickly you're changing your position. Acceleration is how quickly you can make that velocity change. And as I said, just as velocity was the change in position over change in time, acceleration is the change in velocity over change in time. Now, just as with instantaneous velocity, we take a limit and we let the change in time become smaller and smaller and smaller and see what value do we approach. The same thing holds true with accelerations. We let the change in time get smaller and smaller and smaller and see what value do we approach. What is the instantaneous, or over a very small time period, what is the rate at which we are increasing our speed? One more comment. Before, I was writing these down as accelerations in miles per hour per second. I like to introduce acceleration that way because it distinguishes between the two time units. We're changing our speed, miles per hour, and we're measuring how much we change our speed in each second. So it's miles per hour per second. Later on, we'll have units that'll be meters per second, which simply simplifies to meters per second squared. It is still important to remember that this is not the same thing as a velocity. I've seen it many times where people just say, oh, the acceleration due to gravity is 9.8 meters per second squared, so anything falling must fall at a speed of 9.8 meters per second. That's not true at all. As soon as you let something go, its velocity is 0. After it's fallen for a long time, it can fall at velocities much higher than 9.8 meters per second. 9.8 meters per second is the acceleration due to gravity. That means in each second, we speed up our falling rate by about 10 meters per second, or 9.8 meters per second, in each second. So here, we've got a couple of position time graphs. We've got a strobe picture in the left of each illustration, and a dot showing 1 point to represent the location of the cat, or the location of the first 5 positions of the bouncing ball. Notice that in the y direction on both cases, the distance between successive flashes is changing. Now the flashes are at a specific time interval, which means if the distance between them is changing, the speed must be changing. Either we are getting faster or we are getting slower. Here in the case of the cat, we start at the top, and you'll notice the spacing between dots gets bigger and bigger, suggesting the cat is falling faster and faster. Here in the case of the bouncing ball, for the first 5 dots, you'll see that the spacing, we start at the bottom, the spacing gets closer and closer and closer. However, so that suggests that it's getting slower. However, if we look at the position in the x direction, the spacing is exactly the same. So the ball appears to be having a constant velocity in the x direction, while a changing velocity in the y direction. That's very key to projectile motion, which we will start studying next time.